Before I begin, I would also like to thank you, Giovanni, for the invitation to contribute to this wonderful series of talks that you've been organizing this past year. What I would like to talk about today is basically a few recent experiments that we've done on electric control of antiferromagnetic and ferrimagnetic order using spin-orbit torques. This is work that was primarily supported by the National Science Foundation, by the Materials Research Center at Northwestern, and by some of our industry sponsors. And this is the outline. So basically, I will give a very quick overview of three papers, which are listed here if you would like to take a look at the details. So the first two are focused on antiferromagnets, on electrical manipulation of magnetic order in platinum manganese and in iridium manganese 3. And the third one is focused on a ferrimagnetic system. And the key problem that we were trying to solve here in this third paper is to develop a new way of performing directional and deterministic field-free switching of perpendicular magnets using spin-orbit torque. And we did this in a cobalt terbium-based ferrimagnetic system with a vertical composition gradient. So there's no in-plane structural asymmetry in the device, which is the kind of the interesting aspect of it. So these are the three works that I will go through today. And I should mention that Giovanni Finocchio and his team have been key parts of all three works that I will be presenting, basically doing essentially all of the micromagnetic simulations that supported the experiments that I will show. So the background to this is that we are interested in developing magnetic devices for computing, particularly for data-intensive computing. And the problem that we're trying to solve is that essentially AI applications, artificial intelligence or machine learning, whatever you call it, are very energy inefficient these days. So if you look at the state-of-the-art numbers, whether you look at the Google's AlphaGo system and its successors that have been in the news in recent years, or whether you look at more recent numbers from, say, autonomous cars that where autonomous driving systems use a lot of machine learning, the energy consumption of such systems is about 2 to 5 orders of magnitude larger than that of a human brain. So depending on whether the system is doing inference or training, it consumes somewhere between 2 kilowatts or substantially larger than that, even 2 to 3 orders of magnitude more than that if it's doing training. And so this is clearly a problem, particularly with the increasing need to put machine learning systems in edge systems where essentially you don't have the cloud infrastructure to support both the power requirements and the cooling requirements of this systems like this. And if you really look at the basic reason for this kind of very large energy consumption, it comes down to the fact that the way we organize computing systems today, we have essentially a part that is doing the computing, that's doing the logic, that's the processor core, whether it's a CPU, GPU, or a specialized neuromorphic chip. And then you have various tiers of memory that that successively become slower and denser as they go away from the logic chip. So the layer of memory that is closest to the logic, which is usually on the same chip as the logic, is SRAM, the static random access memory, which is very fast but very low density because it has 6 to 8 transistors per cell. And then you have DRAM, dynamic random access memory, that is much denser, so it can store more data, but there is a very large 1 to 2 order of magnitude energy overhead in accessing any data from the DRAM. And so for any application that has large data sets that need to be worked with, and again, machine learning is a great example of that, Actually, what you would like to do is to put all of your data directly on the same chip as your logic. The problem is you can't do that if you have a low density memory that needs many transistors to store one bit of information. And so that's one way of looking at a lot of the efforts in spintronics, and particularly in magnetic random access memory, where essentially the attempt is to store information in a magnetic element, usually in a magnetic tunnel junction, which is a nanoscale magnetic device. And then again, usually you have a transistor in series with that magnetic device that acts as the select element. But you can see that then you basically have a one transistor cell, or one transistor, one magnet cell, which is much more compact than the usual SRAM cell. And so this is it presents a much better scenario for for using this as an on-chip embedded memory, provided you can get it to the large density and high speed and endurance that is required for that kind of memory. So there's been a lot of progress in spin transfer torque MRAM in the past few years. And basically all of the major manufacturers, semiconductor manufacturers, have STT-MRAM either in production or close to production. But there are also challenges that prevent it from really successfully addressing this problem that I just described a couple of slides ago. Just to highlight two of these, one problem is that in order to switch fast using current-controlled switching of these magnetic elements using spin transfer torque, which is the prevailing method today, you need large transistors because they need to drive large currents, and that again limits the density. The solution to that potentially that we are working on is to develop voltage-controlled devices, and I will not talk about that today. Another challenge is that if you think about putting these magnetic elements very close together, they start interacting through dipole interactions because they're ferromagnetic and they all have stray fields. And if you have a very small pitch between neighboring bit cells, then they will magnetically interact, and this causes errors. This is not a hypothetical problem. It has in fact been measured and discussed in detail in some of the highest density STT-MRAM chips that have been built to date. And this will become an even bigger problem if we go after problems like the ones that I described here, where high density and advanced CMOS nodes with tight pitch are required. So a potential solution to that then is to use antiferromagnetic materials, which have magnetic order, but have no macroscopic magnetic moment. So there are no stray fields emanating from them, and therefore you don't have dipole interaction between neighboring bits. So for us, for my group, this is the main reason currently we are interested in antiferromagnets. Of course, there are other reasons as well for terahertz applications and so on. And so because of all of these potential impacts of antiferromagnetic spintronics, there's been a lot of interest in recent years in controlling antiferromagnetic order using electrical means. I'm kind of showing basically the two general flavors of this that have been shown in the literature. This is by no means a comprehensive slide. There are many more interesting works that could have been listed here, but it basically shows the two general flavors. One is using bulk spin orbit torque, so-called nail spin orbit torque, in materials that have particular broken symmetries that allow for the emergence of such torques in the presence of current. And the second group, which are more reminiscent of ferromagnetic spin orbit torque devices, basically rely on interfacial spin orbit torque. So you have essentially heavy metal in contact with an antiferromagnet, and the spin current generated in the heavy metal can basically manipulate the antiferromagnetic order. So we followed a similar structure as the second group, basically interfacial SOT, but unlike most of the works that preceded our studies, instead of focusing on insulating antiferromagnets, we decided to focus on metallic antiferromagnets. There were a number of reasons for this. some of these metallic antiferromagnets are very well known in the semiconductor community because they've been used in reference layers, for instance, of magnetic sensors, as well as of the earlier generation in-plane MRAMs. So it's known how to integrate them on semiconductor, on CMOS technology. They can be sputter deposited at low temperatures. And so in terms of integrating these eventually into a memory or a computing system, this is very promising. So we focused on the platinum manganese material system. So our heavy metal is platinum, and platinum manganese is the antiferromagnet that we used in our first experiments. We had basically a cross structure, which is shown here in the top left, where we passed currents through a bottom platinum layer, and the AFM, the antiferromagnet, was this pillar in the middle. The state variable here, of course, is not magnetization. It is the Néel vector, which is the vector subtraction of the two magnetic sublattices of the antiferromagnet. And essentially, we were attempting to rotate this Néel order. So this is something that we successfully did, again, first in platinum manganese. Representative data are shown here at the bottom left, where we, using opposite currents along the same direction, we were able to switch the device back and forth. We saw an analog kind of memory operation in this device, which we attributed to essentially motion of antiferromagnetic domain walls, where the larger the current that you applied in a particular direction, the larger the resistive or the output voltage change that we measured. The general features of this experiment were all also successfully reproduced in micromagnetic simulations by Giovanni Finocchio and his team. So this was pretty exciting for us at the time. This was the first demonstration of SOT control of antiferromagnetic order in a metallic antiferromagnet, which was again sputter deposited on an oxidized silicon substrate. And this was followed shortly thereafter by several works from other groups, also in various other metallic antiferromagnetic systems. I'm just highlighting two of them here. The first one on the left, which is from Tohoku University, from the group of Professor Hideo Ono, basically studied the same material system, so platinum manganese, but importantly, they also did an additional experiment, which was X-ray linear dichroism, and so they directly also observed the motion of these domain walls in the platinum manganese. And the one on the right that I'm showing here is focused on manganese-3 tin, which is another interesting metallic antiferromagnet, which has interesting topological transport properties, such as a large anomalous Hall effect. So at the same time, though, with all of this work that was going on, there were several interesting studies that emerged and kind of cautioned everybody that's working on antiferromagnetic spintronics, or particularly with electrical readout methods, such as the ones that we were using. These works basically showed that whenever you have a very high current density in these devices, and that's in most of these experiments, the current densities were pretty high, it is possible that you would measure resistive switching signals that have nothing to do with the magnet, that are not magnetic in origin, but actually are from the heavy metals that are used, usually platinum. And this is, in fact, not a new effect. Most likely what is happening in these experiments is electromigration, which is a very well-known effect in the semiconductor reliability community. But this was kind of an important insight, that we have to be very careful in correctly interpreting these electrical switching signals that we're measuring. So with that in mind, we decided to take a closer look at this in the material systems that we are studying. And we basically designed a new kind of layout for our devices that allowed us to study this systematically. So I'm showing this device layout here. Basically, you can see two crosses in close proximity to each other, where you have one cross where you have the antiferromagnetic pillar in the middle, and there's a neighboring cross that does not have an antiferromagnet. So it's essentially a 6-terminal device where we can send currents through the heavy metal layer in various different combinations of sequences, if you will. And we can do two things that are important here. One is we have basically a non-magnetic cross that only consists of the heavy metal in close proximity to the antiferromagnetic device. So we have a possibility of doing in situ reference measurements, which are not affected by large device-to-device variations because, again, it's in close proximity to the actual antiferromagnet. And secondly, we can do differential measurements. So we can do various types of measurements where we essentially do an intrinsic subtraction of the signals from the two crosses. And that, again, allows us to kind of look in more detail and be able to get at the actual antiferromagnetic dynamics that we are interested in. So we chose initially iridium manganese 3, which is a non-collinear antiferromagnet for these experiments, and these are the results that we got. So I'm showing basically only one of the many different variations of experiments that we did on this device, and for the other ones you can refer to the paper that I'm listing here. But this is maybe the most representative of all of them. So what we're comparing here is switching using opposite currents, so currents in opposite directions along the vertical direction in this graph here. Where in one set of experiments, we are sending these currents in the antiferromagnetic cross, so along terminals 2 and 6. So we send currents back and forth here. And then the other one, we send the same current with the same current density along terminals 3 and 5. And then we read out the resistance by basically sending a small current between terminals 1 and 4 and reading the voltage between terminals 2 and 3. So it's essentially a 4-point resistive measurement. So what you see here on the bottom left is that indeed, when we send the current along terminals 2 and 6, we do see switching, which is pretty prominent. It also shows the kind of analog signature of domain wall motion. And when we send the same current along terminals 3 and 5, we do not see any switching at all. And so this was, for us, perhaps the most convincing initial data that showed us that we are indeed performing antiferromagnetic manipulation, and this is not resistive switching from the platinum. We did this over a range of current densities, and we did observe also that if we reach very high current densities, in fact, we do see resistive switching also from the platinum, which is not surprising. But there is a wide range of current densities where, indeed, it's only the antiferromagnet that is contributing to these switching signals. I would like to also show one other experiment that we did. I mentioned that you can do differential measurements on these devices where you do a kind of a subtraction of the signal from the two crosses. This is particularly useful for higher current densities where you may have switching contributions from the platinum, which in principle would be similar from the two crosses, but then the differential signal is more representative of what's happening in the antiferromagnet. And one example is shown here where we basically had a resistive voltage divider circuit, and we basically amplify the subtracted or the differential voltage between the two arms. And we saw, again, very clear switching also in these experiments with pretty large voltage outputs, about 100 millivolts peak to peak, which is because of the presence of this amplifier here. So this is all I had on the antiferromagnetic part of this work. And the last few minutes, I would like to basically switch gears to the ferrimagnetic system that we've been recently studying. And this is work that is still under review. And we recently posted this on arXiv. So here, the problem that we were trying to solve was to develop a field-free deterministic way of switching perpendicular magnets using spin-orbit torque. This is not a new problem. This has been an important problem for the spin orbit torque MRAM community for a number of years, where from the scaling perspective, you would like to have perpendicular magnets, but the problem is that just the symmetry of the structure does not allow you to perform directional and deterministic switching using spin orbit torque if your free layer of the magnet that you're trying to switch is perpendicular to the current. This just follows from the symmetry of the structure. And so there have been several works over the years that have attempted to break this in-plane symmetry using various methods. And I'm just listing some of them here. The most straightforward way, of course, is to just apply an in-plane field. But that's not practical if you're talking about building a memory chip for various reasons. Having that built-in bias field can be difficult to accomplish. There have been attempts where essentially you have an in-plane structural asymmetry in the device, such as a thickness gradient, perhaps, of a particular layer, or a tilted anisotropy induced, again, by the shape of the sample. These work well, but these are harder to reproduce on a wafer scale. So you can make these well on the, in one or few devices, but achieving the same structural asymmetry across a wafer is more difficult to do. Another way that has been shown several years ago was to use in-plane exchange bias to do this, where essentially this external in-plane field was replaced by an exchange bias field. The challenge there being that you have to simultaneously realize this in-plane exchange bias and a stable perpendicular axis of the magnetization in the free layer, which again is difficult, and it was shown also by the same group, by Hideo Ono's group in subsequent work, that it suffered from large device-to-device variations of the exchange bias as the devices were scaled down. So our attempt at this was we were trying to basically develop a device structure that would allow for field-free deterministic switching that did not have any structural asymmetry in the sample of the plane. So essentially a completely symmetric structure when you build it. What we did was the following. So we focused on cobalt-terbium, which is a ferrimagnetic system. And we deposited cobalt-terbium multi-layers, essentially, or perhaps a more accurate description would be a gradient sample, where essentially in the growth direction, we change the concentration of terbium in this material. So we go from a cobalt-rich composition at the bottom to a terbium-rich at the top, or vice versa. And this is something that you can just do by adjusting the deposition powers as you grow the sample. So the result is a gradient sample where you have a broken symmetry along the z-axis. So the composition changes as you look across the growth direction. But of course, there is no in-plane structural asymmetry in this device. One consequence from this broken symmetry along the z-axis is that you have a pretty large spin orbit torque in this structure, a bulk spin orbit torque. And this follows, in terms of symmetry, you can understand it because it has a broken symmetry along the z-axis, and you also have heavy metals within the structure that have large spin orbit coupling. So it makes sense that when you break the symmetry along the z-axis using this gradient, that you would see a spin Hall angle, a spin Hall effect. Interestingly, we also saw what looks very much like a significant DMI, a Zalezinski-Maria interaction with these samples, and we were able to measure this using the droplet nucleation model that has also been used for other systems. And you can indeed see that there is a what looks like a DMI, a chiral field of about 20 oersteds or so for this particular sample that I'm showing. And this field actually increases as you increase the gradient, the concentration gradient of the sample. Now, this, again, in terms of symmetry, makes sense. This has a broken symmetry. The system has a broken symmetry along the z-axis. And so you can expect a DMI that has the same symmetry as the interfacial DMI that has been studied in, say, in heavy metal systems interfaced with a magnetic layer. But interestingly, what's different about this system is that this DMI is present then throughout the entire volume of the sample because it derives from this gradient rather than from a particular interface. And so we refer to this as a gradient-driven DMI for that reason. Now, when we did, we built Hall bars out of the samples, which are shown here, and we did current-induced switching measurements under different in-plane fields. And interestingly, we see that in these devices, we indeed have zero field switching. So you can see that in the absence of any external field, you have a very clear directional switching with a particular current corresponding to a particular end state of the magnetization. And you can basically compensate for that using an external field. And if you apply an external field of about 20 oersteds or so, which corresponds to the same field that we measure in our DMI experiment, you can essentially destroy this directional switching. So this is indeed a field-free switching in a sample that is completely symmetric in plane, that does not have any broken in-plane symmetry, at least structural broken in-plane symmetry. We did similar experiments in a large number of devices that I'm not showing here, but with different directions with respect to the wafer and so on. So we know that there is no unintentional structural asymmetry in these devices. We've confirmed that. And this has been actually remarkably consistent also across devices that we've built on wafers up to 4-inch in size. And here I'm showing 4 representative graphs from 4 different devices measured on a 4-inch wafer that basically show the same kind of behavior, same directionality, and same current densities. So we think that this can be applied also to other material systems and could provide a way towards field-free deterministic switching of spin orbit torque devices that would be scalable to wafer level. This is really all I had. I have the summary here where, again, I'm listing the papers that I just described if you are interested in taking a closer look. And I would also like to, of course, thank all of the team members that contributed to this, particularly my postdoc, Victor Lopez Dominguez, my students, Jie Cheng, Sevde, and Zhen Yi, who was a visiting student for us for about 1.5 years, and our many collaborators, including our chair, Giovanni Finocchio, who did a fantastic job in micromagnetic modeling of essentially all of these experiments that I described today. And I'd be happy to thank and to take any questions. Thank you.